So next, we're going to start the discussion about causality and propagators. So remember that in non-relativistic quantum mechanics, propagators play a very important role. So what is a propagator? So a propagator in quantum mechanics is just a fancy name for the time evolution operator. So as you know that the time evolution operator, u of t, this is the formal solution to the Schrodinger equation, and it's given by e to the power minus I, the Hamiltonian, times t, divided by h bar, but of course, we're taking h bar to be 1 here. So the propagator is the representation of the time evolution operator in the position basis. So in other words, the propagator, which is written by k, and it's a function of x and t, as well as some past position x prime and t prime, but we can take t prime to be the reference time t0. And then it's given by the position, eigenfunction x as a function of t, acting on u of t, the time evolution operator, and then x prime, so this is the bra and this is the ket. So for a free particle, this was worked out in a quantum mechanics course, and I'm just gonna, do the derivation again, but as in an appendix. So this is given by k of x of t, k of x comma t, and then x prime of 0. So if our particle is a free particle, so it's a non-relativistic, free particle, then its propagator is given by m divided by 2 pi I of t. So there's a prefactor times e to the power I think there's a factor of half here. Yeah. Times im x minus x prime squared divided by 2 h bar t. Now, this propagator is non-zero for any value of t, any finite value of t, as well as x minus x prime. So this means that, if two points or two space-time points are space-like separated, this propagator will still be non-zero. And this is not surprising because this is the non-relativistic result. The non-relativistic physics does not know about the speed of light being the upper limit of the speed possible in space-time. So what we can do is that we can figure out, we can make a guess about what would be the propagator for the relativistic case. Now, when we derive this propagator, the expression that we use is the propagator propagates some state from some past point, 0, to some future point, to some future time t, and as initial condition at time 0, we take the value of the state psi, and we then, the propagator essentially weighs the whole thing, and then we integrate it over all space. So what we find here is that we have to integrate here over all space. So I'm doing it just for one dimension, but this can be generalized. And then, we have 2 pi, and then we have double integral, and one of the integrals we have the Fourier transform function e to the power I p x minus x prime, and then we have e to the power minus I p squared by 2 mt. And this is where the Hamiltonian, and there's also an integral over p. And this is where the Hamiltonian, or the energy of the particle, comes in. And what we can do for our guess for the relativistic propagator is that we can replace it by e to the power minus I, and then we can use the relativistic formula p squared plus m squared times t. And then we can work out what the propagator will be. And what you can do is that you can then take the limit where x minus x prime is much, much greater than t. And so that, in units where c equals to 1, the 2 points we're looking at, they are a space-like separated point. So if you look at that, then the propagator, the relativistic guess for our propagator becomes in that limit, so k of xt, x prime, and 0, this becomes exponential minus the mass times x minus x prime squared minus t squared. So we see that, because of this minus sign, for space-like separation, the propagator is rapidly decaying, but it's not zero. So there is going to be some influence of the particle that is propagating outside the light cone. And therefore, it's going to violate causality. So our first guess about generalizing the propagator to a relativistic case was not successful. It violates causality. So let's try something else. So, let's ask the question, what is the amplitude of a particle being created at some point in space-time, and then the particle going off to another point and being destroyed? So this object is given by this function d times x minus y, and this is the vacuum expectation value of phi x and phi y. And what this says is that the particle is created at some spacetime point y mu, and then it propagates to some other spacetime point x mu, where it is absorbed. So this is what this thing is. So we can figure this out. So this is a quantum mechanical expression. So the phi's here are quantum operators. So we can use the Fourier expansion, and in terms of decay and a dagger with exponential, what I'm talking about. And if you plug that in, what you find is d of x minus y is there's going to be two momentum integral k and k1 and k2, and then all the operators will be inside some bracket, but only so of the four combination of operators, only one combination will survive because of annihilation operator annihilating the vacuum. So the only thing that will survive is a of k1, a dagger of k2, this thing, and it'll be multiplied by exponential of I k2y minus I k1x. So now we can use the commutation relationship here, and then this becomes dk1 tilde dk2 tilde 2 pi cubed 2 of ek1, and then we get a Dirac delta function, and we get the exponential factors I of k2y minus I of k1x. And then if I do one of the k integrals, I find this is d of k tilde e to the power minus I kx minus y. So this is what dx minus y looks like. And if we then look at what this function is, say for time-like intervals, so for time-like intervals, the asymptotic form of this function is, so these are left as exercises or tutorial problems, we get an oscillatory function, which is, of course, non-zero. If they're space-like separated, which means they should be causally disconnected, ideally, if we take the difference between x and y, which say is r, to be infinite, we find that it has e to the power mr. So again, it is suppressed but non-zero. So thus we see that this definition of a propagator is still not it still violates causality. So what we should have done is not just like sandwich two field operators between the vacuum. What we should have asked is that the question that we should ask is that whether or not it's possible to observe the field operators if they're spatially separated. And that means that we should have considered the commutator of two field operators sandwiched in a vacuum. So if that is the case, then this is just nothing but d of x minus y minus d of y minus x. So let's see if this is vanishing or not for space-like separation. Let me remind you what I mean by space-like separation. So we have the light cone, and so like this. So this point is say x. If the point y is outside the light cone, then this separation is space-like separation, and that's what we're looking at. So if you're looking at space-like separation, then we can always do a Lorentz transformation such that x minus y squared, for space-like separation, of course, this is negative. And we can always do a Lorentz transformation such that the time component of this difference, this object is zero. In other words, that they are simultaneous. So let's assume that we have done that and we have gone to that reference frame. Of course, this thing is going to be invariant, and our definition of D function also makes clear that this is a Lorentz invariant quantity. So in that case, D of x minus y is nothing but the Lorentz invariant measure e to the power I, and now it's a 3 momentum inner product with a 3 vector. But we see that this integration measure and the limits are invariant under k go to minus k, under this replacement. And since k is a dummy variable, we can always do that. If you do that, then we find that this becomes d of k tilde, and here we get e to the power minus I k dot x minus y. And then we can just absorb this minus sign, and then this becomes e to the power I of k dot y minus x, which is d to the power dy minus x. So thus we see that for space-like separation, this argument does not hold for time-like separation. D of x minus y is equals to d of y minus x. And therefore, for space-like separation, we see that these guys cancel out. So for space-like separation, we find that the commutator of the field phi x and phi y vanishes for x minus y squared less than 0. And that means that causality is preserved in quantum field theory, whereas in quantum mechanics, causality is violated.